Alright, so in this lecture we're going to continue on with our discussion of plates, and we're going to look at some of the governing equations. I'm going to have to split this up into two lectures. We'll get into stresses and curvatures and things, but we're going to leave some of the discussion for a part 2 or a part B of this lecture. So we're going to start with our elasticity strain tensor definition for small strain theory. Epsilon ij is equal to 1/2 partial of ui with respect to xj plus partial of uj with respect to xi, where u represents displacement in the 1, 2, and 3 direction, ij or k, and the x sub 1, 2, and 3 represent positions like x, y, and z. So we're going to dispense with the index notation. We're going to go back and use kind of the full notation. Our displacements u1, u2, and u3, we're going to call displacements u, v, and w in the x, y, and z directions respectively. We're also going to use engineering shearing strains, which are twice our tensorial shearing strain. So, for example, gamma xy is equal to 2 epsilon xy. Well, for this then, we can write down our strains. In the x direction, we would have a 1/2 partial of u1 with respect to x1 plus the partial of u1 with respect to x1, or with our expanded notation, partial of u with respect to x. Similarly, strain in the y direction is the partial of v, the displacement in the y direction with respect to y. Shearing strain gamma xy is going to be equal to the partial of u with respect to y plus the partial of v with respect to x. And we have 3 more strains. Epsilon z is the partial of w with respect to z. Gamma xz is the partial derivative of w with respect to x, and added to that partial of u with respect to z. And then finally gamma yz is equal to partial of w with respect to y plus the partial of v with respect to z. Now, for our case, we're going to neglect the strains that are out of plane, out of the xy plane. So epsilon z, gamma xz, and gamma yz, we're going to assume are negligible. Alright. So if we do that now, we have a set of differential equations. And just to emphasize this, we can start integrating these up and learn a little bit more about our displacement fields. So let's take a look at that top one on the right. Epsilon z is equal to partial derivative of w with respect to z, and it being equal to 0. So if we integrate this partial differential equation, we can find that the function w is just a function of x and y. It's not a function of z. If we go to the next one, we can rearrange gamma xz equal to 0 and find here that the partial of u with respect to z is equal to minus partial of w with respect to x. Alright. Now, since u is a function of x and y, what this implies then is that u is equal to minus z partial derivative of w with respect to x, and potentially a arbitrary function, call it u naught of x and y. And then the third one on the right hand side, gamma yz equal to 0, in a similar fashion here, implies that the partial of v with respect to z is equal to minus the partial of w with respect to y. Right, since w is not a function of z, we can integrate both sides and find that v is equal to minus z, partial derivative of w with respect to y, plus some function v naught of x and y. Okay, now we do have some restrictions that are set forth that we're going to use. I'm going to read some of these out of Ugarel's book. The deflection of the midsurface is small compared with the thickness of the plate. The slope of the deflected surface is therefore very small, and the square of the slope is a negligible quantity in comparison with unity. The midplane remains unstrained subsequent to bending. Plane sections initially normal midsurface remain plane and normal the surface after bending. We're going to have gamma xz and gamma yz negligible, which is the assumptions that we made right here. In the stress normal of the midplane, sigma z is small compared with the other components of stress and can be neglected. All right, so we are restricting ourselves a little bit. And the u naught and v naught represent offsets of the midplane. As far as our concerns right now, we're going to neglect those. Now later on, if I get a chance to talk about composite materials or some different situations, we can incorporate those terms again. But for now, we're going to neglect u naught and v naught. Now let's draw a kind of a sketch of our plate, and we'll get some idea of maybe what's going on here. So this is kind of an arbitrary plate. In order to show this, I'm kind of exaggerating the thickness. Alright, so this dimension, we'll call that T. The midplane is where we're at right now. And on this midplane, we have an x and a y-axis, and the z-axis of our plate going down this way. So the top and bottom surfaces of the plate lie at plus and minus t over 2. Alright, let's get into the geometry of the deformation just a little bit. It's going to be easiest if we look at this as kind of a side view, similar to what we did with our beam in the previous lecture. Alright, so we're going to look at the strain displacement of the plate. So we have the x-axis going to the right, the z-axis down, and that red line is initially vertical before any load is applied. The plate has some loads applied, it gets bent, it gets deformed. We have a vertical displacement from where the midplane started out being to where it is now, and that distance is going to be the displacement in the z direction. That's going to be the distance w. Now along the plate, we were to take a small bit of distance in the x direction, we get a small bit of displacement here. So we can think of this as partial x with respect, and then partial w. So that this angle right here, from where we can draw this horizontal to where this kind of comes out this way, we can consider that angle the partial of w with respect to x. Again, we've, just like the beams, we've used small angle approximations. Now if we think about where a point down here started out and to where it has moved, notice that it has moved to the left from where it used to be it has a displacement that we'll call u, and we can figure out what that displacement is if we think of the distance from the midplane down to that point as the distance z. The angle that I've drawn here and the angle that I have here is the same. This magnitude of the distance u is going to be the hypotenuse times the sine of that angle. Now, with that angle being small, the sine and the angle in radians are about the same. So that's z partial of w with respect to x. And because that has moved to the left, we're going to say that displacement in the x direction is minus z partial of w with respect to x. And in a similar way, the v displacement is going to be minus z a partial of w with respect to y. Alright, now we have a little bit more to work with our strain displacement relations. We have an expression for the displacements. And so our strain in the x direction then is going to be minus z second partial of w with respect to x. Strain in the y direction is going to be minus z second partial of w with respect to y. And here we have the mixed partial derivatives. So let's see, we're going to have partial of u with respect to y, so minus z partial of w with respect to x and y, minus z partial of w with respect to x and y. So that would be minus 2z second partial of w with respect to x and y. Now, if we recall our discussion of the beams, we said that for a beam, we had the strain in the longitudinal direction is equal to minus z over rho, or it's equal to minus z times kappa, where kappa is the curvature. We can do the same sort of thing here, where we have curvatures in these various directions. So that's a curvature in the x direction, curvature in the y direction, and we can have a curvature term kappa xy for the plate. Alright, so just to formally write these down then, curvature in the x would be the second partial of w with respect to x. Curvature in the y would be the second partial of w with respect to y, and this mixed curvature term kappa xy would be equal to second partial of w with respect to x and y. We can also find various radii of curvature. We want 1 over rx is equal to this kappa x, 1 over ry is equal to kappa y, and a mixed term 1 over rxy is equal to kappa xy. I don't think I spelled that right. It's supposed to be radii of curvature. And in fact, what I have then, to make this the right way, I need to get rid of these two. Right, so those are the various radii of curvature terms. Now, since we have these strains that are written in terms of these radii of curvature, and we can do a Mohr circle of strain, we can also do a Mohr circle of curvatures. And so I have a lecture on the Mohr circle of strain, but very briefly, we can plot our what's known as our x point, which is our epsilon x comma gamma xy over 2 term, our y point, which is a epsilon y comma minus gamma xy over 2 term, and the center of our circle, which would be epsilon average comma 0. If we factor away the minus z, we would have our kappa x comma kappa xy, our kappa y comma minus kappa xy, our kappa x plus kappa y over 2 term comma 0. We could plot, and I'll just put in here a minus z multiplying all these terms. And with our with our axes here, this being our normal term, this kind of being our shear term here. If we have an off-axis term here, a kappa xy term, in general we might be down at this position. This would be our x position, this would be our y position. We could define a principal directions for our curvature. So you can take a plate that has an arbitrary curvatures in these, kappa x, kappa y, kappa xy, and you can find principal directions of curvature. You can find an angle to a principal direction of curvature. Okay, so that's kind of interesting. And if we are in a situation where the curvatures are equal and there is no shear term, there's no kappa xy, then what we have is the midplane of our plate being formed into a spherical surface. Alright, so that's kind of interesting, and just kind of a short little aside. Alright, so now what we're going to do is we're going to apply our stress-strain relations to see what we can do to find our stresses in terms of these curvatures, and we're going to introduce another term. It's going to be a moment per length term. Alright, so here's our 3D Hooke's law. Again, there's another whole lecture that I made on deriving 3D Hooke's law and discussing how that works. But here's our strains, epsilon x, y, and z, in terms of the stresses, the modulus of elasticity E and Poisson's ratio nu, and our shearing strains, gamma xy, gamma yz, and gamma xz, in terms of the respective shearing stresses, and the shear modulus G, where the shear modulus G can be written in terms of the other two constants for an isotropic material as E over 2 divided by 1 plus nu. Now for our situation, we mentioned that we were going to neglect sigma z. And in that case, with sigma z is equal to 0, we can invert these two epsilon x and epsilon y equations. Again, I've done the algebra for that elsewhere. So I'm going to write down the results that sigma x is equal to E over 1 minus nu squared epsilon x plus nu epsilon y, and sigma y is equal to E over 1 minus nu squared epsilon y plus nu epsilon x. And of course for our shearing stress, if we rearrange that, tau xy is equal to shear modulus G times gamma xy. And since G is equal to E over 2 divided by 1 plus nu, we can write all of these equations in terms of the modulus of elasticity and Poisson's ratio. Now these strains themselves, we've shown how they can be written in terms of curvatures. And so we can directly do that, and let's do that on this page. So here we have a minus z. We have these coefficients out in front. We have kappa x plus nu kappa y. We have minus z e over 1 minus nu squared. We've got a kappa y plus nu kappa x. And then on this term, let's see, we have e over 2 divided by 1 plus nu. We have gamma xy, which is equal to minus 2z kappa xy. This 2 and this 2 go away. So we have minus z e over 1 plus nu times this quantity kappa xy. We can even write these in terms of these partial differential equations that we had for w. And let's go ahead and do that. Alright, so in terms of the second partial derivatives, because we know that we can write these curvature terms in terms of those, we can write our stresses in terms of the second partial derivatives as well. So we have minus z e 1 minus nu squared, second partial w with respect to x squared, plus nu, second partial w with respect to y twice. Likewise for sigma y. And for tau xy, I'm going to do one extra thing. I'm going to multiply the top and bottom of that equation by 1 minus nu. So if I want, I can write it this way as minus z e divided by 1 minus nu squared times 1 minus nu, second partial of w with respect to x and y. From these equations, we can see that these stresses, all of these stresses right here, vary linearly through the thickness. Very similar in fashion to a bending stress in a beam. Okay, so it's proportional to the distance from the midplane that we've defined, goes through the middle of our plate surface. Let's take a look at a sketch of one of these distributions for our plate. And so I'm going to kind of draw a sketch. Here's the view of our plate. Now here's here's our x, here's our y, and then there's our z direction. There's the thickness of my plate. And I'm going to look at this edge that's kind of over on the right side. Alright, so I know my stresses vary linearly with the distance from the midplane. So they're going to be the maximum on the extreme surfaces of the plate, and they're going to taper linearly to the midplane like this. And similar to a beam stress distribution, we have a very similar looking picture. So the way we have our coordinate system set up and the negative sign of the equation, we have a compression on the bottom and a tension on the top that goes across here. Alright, now here's where things get to be a little bit tricky with plates, and it has to do with evaluating the stresses through equilibrium. Okay, I'm going to take a look at a small rectangle, little stress block that's on the bottom part of the plate. That's meaning it's on the plus z part of the plate. And on this surface, this being the x direction, I have a little bit of dy, and I have a little bit of dz dimension this way. So my dA, my infinitesimal area element, has a dy and a dz component. Now acting on that is some stress. Alright, so my stress is pointing in the direction I drew my arrow on the bottom half of the plate for a positive moment. So I have a little bit of force that is in that spot, and that little bit of force is due to that stress, sigma x times that distance dA. course, that dA is the d, let's write it this way, dz by dy amount of distance that we have there. I have a contribution to the moment on that edge of the plate. The contribution to the moment on the edge of the plate is determined by integrating these stresses through the thickness of the plate and along the width of the plate in the y direction. Now here's what gets to be a little bit tricky. I am only going to do the integration through the thickness. Right now I am not going to worry about the integration through the width of the plate. So what I mean by that is if I want that moment I want to try to avoid some confusion. If a total moment would be an integral over the entire area, so that would be an integral of a moment arm distance of z times the df. It would be the z times sigma x dA. If I wanted that total area, if I wanted that total moment, I would integrate this with respect to the area. What I'm going to do though is I'm only going to integrate this term with respect to z. So if I do that, I have an integral from z is equal to minus t over 2 to plus t over 2 of z sigma x dz, and then I have that term dy. I'm going to define this term right here as the term mx. Now, the moment is an area integral over the whole thing. Let me back up. I need to be a little bit more careful how I do that. I guess we can use this that I have right here. The total moment would be an area integral from over y. Okay, after we do this, but this integral through the thickness, I'm going to define that as mx. So we have here the total moment is equal to this term mx times the integral over dy, from wherever to wherever. We're not going to work with total moments in plate theory. We're going to work with a moment per length. So we're going to get rid of that y dimension. Okay, again, just to make that clear, the m sub x term that I'm going to start using now is a moment per length term. And what's even a little bit more weird is when you take a moment divided by length, you get units of force. But you can think of it as a distributed moment on the edge of the plate. It's going to be defined as this integral from minus t over 2 to plus t over 2 of z sigma x dz. In a similar way, we can also define my and mxy. So if we want, we can express this as a vector terms mx, my, and mxy equal to integral of z. Here we have the stresses sigma x, sigma y, and tau xy dz. And just for completeness, if we again want to sketch our plate, x, y, and z directions. Our stress sigma y would be out this way, stress sigma x would be this way, and tau xy, defined by our coordinate system as positive, would be in these directions. Now, although we've neglected the strains through the thickness gamma xz and gamma yz, it's going to turn out that we're not going to neglect the stresses and their contributions to the vertical shearing forces. And so, again, based on our coordinate system, we can define shearing stresses this way. This would be tau xz, it's on the x face in the z direction, and we can have a shearing stress that goes down this way. It would be tau yz, it's on the y face in the z direction. And in a similar way, we can define some shearing forces per length. It's qx and qy as an integral from minus t over 2 to t over plus t over 2. Now we don't have the z term because we don't have a moment anymore, but it would be these two shearing stresses respectively, tau xz and tau yz, integrated with respect to z. So qx and qy are forces per length. Now we know what our expressions for the stresses are, in particular the normal stresses. We can write them either in terms of the curvatures, or we can write them in terms of the second partial derivatives of w with respect to those spatial coordinates. So let's set that up and let's take a look at those. Alright, so let's take a look at one of these terms. I think that will be enough to get our point across. Let's look at the mx term. It's equal to this integral minus t over 2 to t over 2 of z sigma x. Okay, so now I already have a z in here, so it's going to be a minus z squared e over 1 minus nu squared, second partial of w with respect to x, plus nu second partial of w with respect to y. And then we have the dz. Alright, so some things do not depend on z. In fact, the only thing that does depend on z is the z term. So let's bring all this other stuff out in front. Alright. And when we integrate z squared, we get a z cubed. Okay, so let's just look at this term. And it's going to be divided by 3 and evaluated from minus t over 2 to t plus t over 2. Now, 2 cubed is 8, so we're going to have a t over 8, t cubed over 8, minus a negative t cubed over 8, all of that over 3. And so this is 1/4 t cubed over 8. This would be, 1/4 t cubed over 3. This would be 1/12 t cubed. So mx is going to be equal to minus e 1 minus nu squared t cubed over 12, second partial of w with respect to x, plus nu second partial of w with respect to y. And again, those could also be written in terms of curvatures if we so desired. Other terms could be written in the same fashion. Alright, now this term, if you notice the coefficient out in front, e 1 minus nu squared t cubed over 12, we are going to define this as the flexural rigidity of the plate. So d is going to be equal to e t cubed divided by 1 minus nu squared over 12. Now if you think back, we'll see this when we get into deflections, but if you think back to what we had for the square beam, it was e t cubed over 12, but now we have an additional term of 1 minus nu squared. Okay, that term is going to be a little bit less than 1, so that's going to make the rigidity of the plate a little bit higher than the rigidity of the beam, because the dimensions of the plate constrain the deformation in the transverse direction. Okay, so just by moving from a plate type geometry away from a beam, we have a little bit more inherent stiffness of that structure. Right, so when we do all of this, then we can write these moment per length terms. In terms of this rigidity and the second partial derivatives and Poisson's ratio. Of course, we can also write these in terms of the curvatures as well. Of course, on this last term, we have that additional 1 minus nu, so that we can make that common term for the rigidity. Alright, let's go back to stresses now. I'm not going to paste this, I'm just going to write it down. Now recall that we had sigma x is minus e times z over 1 minus nu squared. The second partial of w with respect to x plus nu, second partial of w with respect to y. And so if we wanted to then, well, let's do it this way. We also have the term mx that is equal to minus d times this common term that we have right here. And so we can rearrange these terms. We can eliminate the partial derivative terms and write the stresses in terms of this moment per length mx. Let's see if we can do that. If we solve this first one and substitute it into here, or solve the second one, substitute it in the first, so we'd have sigma x equal to minus e z 1 minus nu squared. Here we would have this term in the parentheses equal to mx over minus d. Of course, d we just said was e t cubed over 1 minus nu squared times 12. Let's see, the 1 minus nu squared terms cancel, the e's cancel, the negative signs cancel, and let's see what we're left with. 12 mx times z over t cubed. Okay, likewise, sigma y is 12 my z over t cubed, and tau xy is equal to 12 mxy z over t cubed. Alright, I think that's enough for this one. What we're going to look at next is an application of equilibrium equations with these different stress values. And I think after that we'll be able to get into governing the flexion equation of a plate.